Hello everyone, my name is Sergey Yastrebov, I'm a community lead from Footbook Developer Circle Moscow, and today I welcome you at the last day of Deep Learning Online Meetup. If you didn't see previous presentation where we talk about audio separation from multiple speakers, content recognition from music, generative models for survey, all presentation about self-driving cars, check out our YouTube channel. If during the presentation you would have some question, please use live chat. If you would have some question while watching this presentation on record, use comment because live chat will not be available after live session is over. And now let me introduce our today's speaker, Gianluca Detommaso, who will talk about variational methods for uncertainty estimation. Welcome, Gianluca. You can start sharing your screen and start when you're ready.
Okay, thank you, Sergey. All right, let's start. In this talk, I will talk about variational methods for uncertainty estimation. This is going to be a review talk. And in machine learning, there are really many methods with many variation and under many different names. And under this presentation, my focus is going to actually be to find the common root. Where do these methods come from? And we are going to see, although the talk could be slightly technical, we are going to see that they all come from a pretty simple common framework. But first of all, I would really like to talk about why. Why would you like to estimate uncertainties? Well, this is uncertainty is really useful in a lot of different situations. And here I just picture 3 examples. You can see the picture on the left, top left. This is let's say a self-driving car. And of course, when a self-driving car has to do a maneuver, well, it needs to have a measure of the risk associated to the maneuver, a measure of the uncertainty, right? It's a matter of safety. And actually, the uncertainty estimation here is very important. You don't just want to get some sort of very approximate and shaky uncertainty estimation. Well, it's a matter of safety. You need to be quite sure of what you're doing. Another example on the top left, on the top right, you can see, let's say, stock market. Stocks go up and down all the time, and if you want to make money, you want to estimate the probability that the stock will go up. You want to predict that event, or down, right? And on the bottom, we have a project that I actually was involved and that's why I put it in. This is the automatic construction, 3D printed construction of a bridge in Amsterdam. And the project was about understanding whether defects on a microscopic structure in the material could affect the, let's call, performance of the bridge. Substantially, you would like to understand whether the bridge would go down or not. And of course, there is an uncertainty around it. There is a probability to estimate. And in order for the bridge to be solid enough, to be available, you need to make sure statistically that this probability is small enough. Okay, so this is only very few examples. There are so many, but I hope I gave an idea why probability and uncertainty is very important to estimate. So, what is the main tool of statistician for describing uncertainty? Well, one of the favorite tools, in fact, is called Bayes' theorem. And Bayes' theorem, what it does somehow is putting together your own knowledge about some parameters x and the data information, what I denote by y, the data. You put these two quantities together to work out a posterior probability of your parameters, which means I have my own knowledge about x. I merge it somehow with my knowledge given by the data. I combine these two elements to have an understanding of the uncertainty of the parameters after I have observed the data. And the Bayes' theorem tells you that the posterior distribution here that I denote on the left as pi of x given y is proportional to the likelihood function, which is the probability of the data given the parameters, times the prior distribution, which is my knowledge of the problem. And this is something that is very important in statistics, in particular in Bayesian statistics. And the goal eventually is going to be to estimate this left-hand side, estimate the posterior distribution of the parameters given the data. So let's go forward. Now, if you've seen the formula before, matter of factly, you could apply the logarithm to both sides of the equation and get that the log posterior on the left is equal to the log likelihood plus the log prior plus a constant that we don't care about. And let me just for 1 second give some little assumptions. Let's just really reduce this to a small example. Suppose for one moment a very common dependency structure between the parameters x and the data y. Suppose indeed that the data is given by some function of x plus some noise, right? This is a very common. F could be any sort of model, linear regression, logistic regression, neural network, whatever sort of model that you have in mind. Suppose that this is the relation that links your parameters x with the data y. And eventually, let's also say that the prior distribution, let's just assume it to be a Gaussian with some precision lambda, all right? So we have this sort of additive Gaussian noise model for the data and this Gaussian prior for the parameters. So if you then plug this assumption in the equation above, well, the log posterior probability just becomes this right-hand side here, which although might seem scary, if you look closely, this first term here is exactly a mean squared error. So it's the difference between the data and the function f in norm squared. And this is a very, very common loss used in machine learning, used in statistics. And usually you would use just this term to estimate the maximum likelihood estimator, the MLE. And plus, what the prior distribution does is giving you a regularization over the parameters for your loss, right? So this little calculation shows you, in fact, that if I want to calculate the maximum of this posterior, log pi of x given y, if I want to find the x parameter that maximizes the posterior, that is the parameters that is the most likely, given the data and my prior knowledge of the system, well, this is in fact equivalent to maximize this mean squared error loss regularized by this term over here. And this, in fact, this very, very simple example draws the connection between a Bayesian statistical method and a frequentist method. But so what we are doing here, in fact, is maximizing the posterior, right? We said we want to find the most likely parameter, the one that best fits the data and our prior knowledge of the system. But the reality is that Bayes' theorem allows you to do more than that. There is more than the maximum. There is more than just a point estimate, one single number. In fact, what do you do with one single number, right? In some application, okay, you have a number, but what does that tell you? If you don't have a measure of the uncertainty around that number could be totally useless for making any sort of future decision. So the goal here is going to be to quantify the uncertainties around our estimates. And well, there are all sorts of possible methods borrowed from statistics to do so. One very classical one is sampling via MCMC, which is Markov chain Monte Carlo. Now, this is a very powerful method. It's a great method, in fact, and it's correct asymptotically, which means that if you keep running your algorithm for an infinite amount of time, you will get correct results. But the fact is that in practice, potentially, it can be slow, in particular for high-dimensional problems and for big data. So in machine learning, people prefer often to revert to what's called variational methods, which are based on optimization. And these variational methods are for the purpose of estimating uncertainty. So in this talk, I will review a few. And specifically, I will want to talk about variational inference, automatic differentiation, variational inference, normalizing flow, and something less common, but which I particularly care about, and it's called Stein variational inference. So let's start by variational inference. Okay, variational inference VI. What is this? Remember, our purpose is to estimate the posterior distribution pi, right? So we want to approximate the posterior pi given the data y with a generic density that we will denote by q, right? This density can be anything you want. It's just a generic approximation. And the purpose of this variational inference algorithm is going to be to find a density q that somehow is close enough to pi. And under this very consideration, you want to find a q that is close to pi. Well, when I say close, you need to have a measure of how far apart are these probability distributions, right? And the most common measure that people usually use in machine learning is called Kullback-Leibler divergence, for short KL divergence. And it works as following. The KL divergence between Q and pi is the expectation under Q of the logarithm of the ratio between Q and pi. All right? So without looking too much into the details of this mathematical formula, just know that if Q is exactly equal to pi, then the scale divergence is 0. So you found, and in general, the KL divergence instead is greater than 0. So if you can minimize the KL divergence, it means that you are getting a density Q that is as close as possible to the posterior pi. All right, now suppose that we cast this density Q to be a parametric density, which means Q actually depends on a parameter that we call theta, okay? So in this case, what could we do? Well, if we assume a parametric dependency from theta, we could just look for the parameters theta that minimize the KL divergence, in some sense, really the distance, although this is not technical. Distance in this case is wrong. But you can look for a theta that minimizes the divergence between q and pi. So you get q as close as possible to pi. And in this way, you can get a parametric approximation of the posterior. Now, to be honest, in variational inference, this is not exactly what's done. People don't consider exactly the elbow. They consider a lower bound called elbow. And you maximize the elbow, you don't minimize the KL divergence, but these two problems are very related. We are not going to talk about it just now. Although you can really just think that eventually what you want to do is minimizing this quantity over theta. Right, so we have said that we can take a parametric approximation of the, well, a parametric approximation of pi called Q theta. But what sort of parametric form can we give to Q theta? Well, what variational inference does, at least the very standard variational inference, the most common use, is taking Q theta to be a diagonal Gaussian approximation, which means Q theta is a Gaussian, a normal distribution, with mu to be the vector mean, and a diagonal covariance metric specified by this parameter sigma. So mu and sigma are just the component of this vector theta that I denoted above, which denotes all the parameters of my distribution. Now, just one side note, note that this assumption where you take a diagonal approximating distribution is called the mean field approximation. And what it's telling you is that all the components of your systems, all the components of your parameters, so remember x, are assumed to be independent. Of course, this is a very strong assumption, right? I mean, most likely the component of your parameter space are not going to be independent. But it turns out that a diagonal approximation like that is very scalable, which means that you can use this variational inference algorithm for very high dimensions of your parameter space and the high dimensional data. So if you just have these few points, well, in some sense, this is what defines a variational inference algorithm, right? So just to sum up, we want to approximate the posterior, which shows a divergence criteria. We said that we take a parametric density, q theta, and we minimize for that. And as q theta, we choose a diagonal Gaussian. This gives you variational inference. What could we do differently, right? So let's move forward. Automatic differentiation variational inference. What's the difference from the, this is another method if you want. What's the difference from the method before? Well, you start in the exactly same way, right? You want to approximate pi with a density q. You consider exactly the same KL divergence between q and pi. And again, you will take some sort of parametric form, but this time is going to be slightly different. So rather than taking directly q to be a parametric density, what happens in this case is that you take q to be a push-forward map of some basic density q0, where q0 is a very simple density, for example, a standard Gaussian. And t instead is some sort of transformation. Is a transformation that transforms this density q0 into what is going to be q. And well, maybe transformation or transport map or whatever you want to call this term t is not very familiar to you, but eventually what this is just a change of variable, really. So this formula here is just the change of variable of a density q, nothing else. So as you see, you have this term and the gradient and the determinant of the gradient term that takes into account the change of volume. Okay, right. So we said we are going to take q as a transformation of some very easy density q0. And rather than directly parameterizing q, what we do is parameterizing the map t, this function t, the transformation. So now, instead of having q equal q theta, what we have is that the transformation t is equal to some t theta. And we will assume that this transformation is invertible so that we can actually apply this change of variable formula. All right, so let me assume that. Then what you can do simply is, again, you want to minimize the KL divergence over the parameters theta. But remember, this time the parameters theta are not anymore the parameters of the distribution directly. They are the parameters of the map T, right? But the framework is exactly the same. You're still minimizing the KL divergence with respect to these parameters. And it turns out that you can rewrite very easily this left-hand side as the right-hand side. So this is an argmax over theta of this formula here that we will not look into directly, but you can just see here that here you are trying to somehow maximize the posterior itself, and with the right term, the second term, is a regularization term that keeps into account the change of volume of the distribution. All right, so with respect to before, once more, what we've done is rather than parameterizing q, we are parameterizing a map, a transformation t, and minimizing over the parameters of that transformation. So you find a transformation that best transports or transforms a density q0 towards pi. Cool. So as you can imagine, as before, we haven't yet specified the form of the parametric transformation t theta, right? So very, very analogously to what variational inference does, automatic differential variational inference again deals with Gaussian approximation. So what's going to happen is that you take this q0, this very, very simple density, as a standard Gaussian, and your transformation is going to be a mean shift and the scaling of this standard Gaussian. So your transformation t is just going to be mu plus sigma x, where this symbol here just means element-wise product. And again, mu and sigma represent the components of this vector theta. So this formula is exactly equivalent to the variational inference method that you had before, with the advantage that since you could express this left-hand side argmin of KL as this right-hand side argmax of this term, you can actually employ automatic differentiation and get your gradients with backpropagation easily. All right, so with this sort of setting, which in fact is equivalent to the setting before, at least from a theoretical perspective, what you have achieved is another algorithm, which is called automatic differential variational inference, ADVI. All right, so as you can see, really, these are different names, but the common framework can be expressed very easily in a few points, and it is not that difficult if you think about it for a while. Now, okay, one could say, cool, very cool. Now we have expressed this approximation through this parametric transformation t theta, which eventually is very simple, right? It's just a mu plus sigma x. What would happen if I complexified this transformation? Well, as you can imagine, if you use a very, very simple transformation, the approximation that you can get, well, it can be probably very scalable, but not super complex, right? Maybe your approximation is not going to be super accurate. And in fact, this variational inference and automatic differentiation variational inference methods only approximate the posterior pi with a Gaussian distribution, a multidimensional Gaussian distribution, all right? But this transformation that we just defined will give you a Gaussian distribution in output, which means that, well, if the posterior is not very Gaussian, your approximation may be not very good. So what happens if we complexify the transformation? Well, this is, in fact, the idea behind the normalizing flow. Normalizing flow is very, very, very similar to automatic differentiation variational inference. The difference is that instead of using that linear transformation that I showed you just before, you will use something based on neural networks, which are known to be very complex, can represent can approximate very complex relations between input and output, and also here can be used to approximate this transformation. Well, to define this transformation. So again, the framework is very, very much the same. You have a posterior distribution pi and an approximating density q. We consider the KL divergence to measure the divergence, or how far apart are the densities q and pi. Again, we are going to take the variational distribution, this approximating distribution q, as a transformation of your simple distribution q0 with a transformation that is parametric and invertible. Then we have exactly the same formula here to minimize. And the only difference, as I said, is that instead of the simple transformation, you have something more complex. So in this case, very, very much like in deep learning, what happens is that the transformation T is a composition of layers. And the layers in this case are simple transformations. So T1, T2, TL up to some capital L, which defines the number of layers. Well, all of these are very, very simple transformations given an input X. So the transformation, the generic transformation TL, one of these, basically, we parameterize with a parameter theta. And we say that this transformation is going to be invertible. Well, we define it to be invertible. It has to be to satisfy the theory. And we will base it on neural networks, although I will not specify how. And again, our initial distribution we will cast as a standard Gaussian. It could be something else, actually. It's not very important, but it's the most simple choice that we can take, probably. And well, according to how you define the architecture behind the neural network, you will have different methods that in machine learning are called under many different names. For example, you can find the autoregressive flow method. It's if you define triangular maps. You can have a real MVP if you split your set of coordinates. Invertible neural networks are also an example of a real MVP if we want, and there are others, right? So I'm not going to talk through this, but just know that the common framework is the same. What changes here is how you define the architecture behind this simple transformation TL. And all of these 4 points will give you a normalizing flow algorithm. What's the advantage with respect to before? Well, the advantage is that your transformation is much more complex. Therefore, you can approximate your posterior distribution not only with the Gaussian distribution, but with more sophisticated approximation, right? What is the drawback? I mean, we shouldn't really only talk about advantages, also of drawback. Well, in order to define a transformation based on neural networks, you're going to use many more parameters. And probably this is not going to be very parametric efficient. And as we know, when we try to find when we try to minimize a loss function when we have neural networks, this is not an easy task because your landscape, in this case the KL divergence, is going to have many local minima. So what could happen and what will most likely happen is that you will find some parameters that are very good locally, but are not the best parameters that you can find. So your posterior approximation Q is going to be perhaps good, but if you're lucky, let's say. It all depends on the optimization algorithm that you're using behind to minimize the scale divergence. And well, it's really a trade-off here because you're complexifying your map, you're complexifying your method, but you're making the inference more difficult. So what do you value more? Do you value more a simple algorithm like a simpler algorithm like ADVI? Or do you value more complex transformation and a more complex approximation? This will depend on your own business problem, and you will need to make this choice. Okay, so this is a normalizing flow. We have seen that we here use a parametric approximation. We can complexify the transformation and so on. All of these examples that I talked about so far use parametric approaches, though. As you see, there is always a parameter theta over which we optimize. Now, this is probably the most familiar approach with machine learning, but I would also like to emphasize some other sort of method that use non-parametric variational information. And this is called Time-Variational gradient descent. Maybe I'm slightly biased because I also worked on this algorithm, but it works as follows, in fact. So you have, again, the framework is exactly the same. We want to approximate the posterior pi with the density Q. We consider the same KL divergence. Now, the difference is the following. We will not have anymore a parametric definition neither of the density Q nor of the transformation T. So again, though, we will define Q to be a transformation of some simple density Q0, exactly as for normalizing flow. Remember, this transformation is just a change of variable. And again, we take the transformation to be a composition of simple transformations. But in this case, the simple transformations are not going to be anymore the layers of a neural network function. They're actually going to be some small shift from the identity function. So every single transformation here is going to be x plus some small step where epsilon is something small. And this Q is a perturbation direction. So what you're saying here is that you are moving your x, let me say your particle x, in a direction q. And this is exactly what you do in optimization if you want, because you move, you update in your, for example, in your gradient descent algorithm, you will update your current position x with some perturbation direction q and a small step size epsilon. And the same concept here happens, but to estimate the posterior distribution. So just not to lose myself into details, well, we take this, all of this simple transformation to be x plus a small perturbation with direction QL. And all of this QL, we take them to be defined into a reproducing kernel Hilbert space, where we say the kernel characterizing the space is called K. Now, we don't need to go into the details of this, but just know that this space is here allowed to define a very wide, it contains a wide definition of functions. So you can really use a lot of different transformations. A lot of different transformations are within this space, according to how you define the kernel also. All right, so what happens here? Now we have a non-parametric definition of our map, and it can be shown that the functional negative gradient direction of the KL divergence, so it means that if I want to take in some sense the functional gradient direction of the KL divergence, well, this is given by the following formula, which is explicit. Like QL is directly, in some sense, the negative gradient of the KL divergence. So you're really doing some sort of functional gradient descent algorithm. So QL is going to be given by this this formula here, which is explicit. You have the gradient of log pi weighted by this kernel K plus a repulsion force, which is this gradient of K. And all right, we should also specify that now this density QL is the transformation of the density before, where you define the initial density to be the standard Gaussian with mean 0 and covariance matrix identity. Now, so this is an iterative algorithm, right? You basically apply this transformation Q every time, and you converge towards a density Q that is closer and closer towards your posterior pi. And this is exactly, if you haven't really figured it out yet, this is exactly what happens in optimization too. So basically, this is a gradient descent method that not only allows you to find the best estimate, the mode of your posterior, but also the uncertainty of your estimation. And this is what I say here. SVGD, this is algorithm, is an ensemble gradient descent optimization. And I will want to give you just a very simple snapshot of this algorithm, just to convince you that it is very simple. In fact, that's it, right? So assume that you have some particles at any steps of your algorithm and a step size epsilon. All you need to do, exactly as in gradient descent, you need to update each particle xi with this direction QL, where QL is just an empirical approximation of the average of the formula that I expressed before. You can go back and check in the video, but this is exactly the formula you had before, where we substitute to this expectation an empirical approximation, just an average, for an ensemble of particles xi. All right? So again, altogether, these particles will move, and they will affect each other, and they will move towards the configuration of your posterior distribution. So if you had only one particle, this particle would go to the mode of your distribution. So one particle Time-Variational gradient descent reduces exactly to gradient descent. But if you have more particles, you can actually capture the uncertainty of your distribution. All right, so I really would like to show you this with a picture. If you're not familiar with this sort of diagram that you see here, this is just the contour of some distribution. In this case, it's going to be my posterior distribution pi. And imagine that you're basically seeing this from above, right? This is some sort of mountain. You see it from above, and the yellow part is the highest part, and the blue part is the flat part of the mountain. And that's it. What we would like is to get some particles that somehow start from our initial density Q0, in this case a Gaussian, and sequentially move towards this shape to really represent and approximate the posterior. So this is what's going to happen. These are samples from an initial Gaussian distribution, as you can see. These are just the green particles taken from another distribution. And what you will want to see, once again, is that these particles sequentially move towards this shape. And this is what's happening here. As you see, in a few steps, these particles rearrange their configuration and move towards the posterior. They become samples from this posterior. And they can be used to approximate your posterior distribution as well. All right, just let me give you some more fun example, just really for the fun of it. And suppose that you have a multi-Gaussian here, a multimodal Gaussian distribution, where well, I tuned it to be a phase. So this is just nice. And imagine that this is even changing over time. It's actually winking this posterior distribution, right? So your distribution is changing over time, and you would like really your algorithm not only to infer the distribution, to approximate the distribution, but also to track the change over time. And just to give you a really just fun example, this is what's happening here as well. You have, again, the initial configuration of particles, and as you can see in the video, the particles not only manage to approximate density, they also follow the changing shape, and eventually they represent exactly the distribution that you want, this winky sort of boat man. All right, so just to sum up what we've seen, we have reviewed a few methods, all to approximate posterior distribution to express uncertainty measure. And here are a few references about the main papers. First is about automatic differentiation, variational inference. Then you have normalizing flow, Time-Variational gradient descent, and finally my own paper about Time-Variational, where we improved the Time-Variational gradient descent to a second-order method. So we improved the optimization part to be second-order Newton method, so much faster. And that's it. Thank you for your attention.
Thank you, Gianluca, for your great presentation. I think we will share some additional materials in the comments after live session just for better understanding of today's topics, because there was a lot of math and some people might find it kind of difficult. Let me check if you have some question in the live chat or in the comments. Just a second. No, we don't have any question yet. Maybe some people will ask some question later after reviewing today's topics more deeply. Thank you again for your presentation and for your time. Don't forget to like this video if you find it interesting. If you have any question while watching this video in the record, please use comments and share this video with your colleagues and friends who might be interested in today's topics. That's all for Deep Learning Online Meetup. Thank you everyone who helped to make this event happen. Amazing speakers, experts, community leads, and everyone who watched, liked, and shared these videos. Stay tuned for more events in the future, like our Frontend Online Meetup that's gonna start on October 15. It also gonna be in 3 days. So check out social networks and developer circle for more information about it. If you can understand Russian, you can find more useful videos on our YouTube channel, like video about system design, JavaScript, and Bitcode solution. And that's all for today. Have a nice time and see you all in the next meetup in October. Bye.